Okay, let me share the screen. All right, can you see the screen, everyone? Let me know.
Yes, I can.
Can't hear you properly. Okay. Yeah. Can you see the screen? Is it visible?
Yes.
Okay, perfect. Perfect. All right. So let's start. Yeah, let's start. Okay. So today we are going to start a new topic of uh, matter physics, right? It's related to temperature and it's essentially called thermal physics, right? Thermal physics. And we'll start our discussion with the topic of temperature, right? But before we get into temperature, we need to understand the molecular nature of everything, right? So which you all must be familiar with by now because I have used these examples to explain multiple things. Even in the last topic, when we were doing pressure, uh, we used the molecular uh, nature of gases to understand pressure as well. So we'll try to understand very quickly first the molecular nature of matter. So we know that we have three uh, we have a lots of different types of matter, states of matter. There are many states of matter, but there are three that are very significant to the basic understanding of physics, which is solid, liquid, and gas, right? Now we can understand all these three using a molecular picture. And we say that, for example, let me start with a solid. We say that the solid, for example, if it's any solid material, it's made up of atoms or molecules, right? And the atoms or molecules in a solid, they are very closely packed, so closely packed that all they can do is perform very slow vibrations, uh, but they cannot change their positions, right? The positions are fixed. They can perform. So, for example, if I take this atom, it can oscillate or vibrate about its position. Very small vibrations can only be performed. And then you have liquids. Liquids are slightly loosely packed, right, compared to solids. They have some space in between them, and so they can change their positions very so slightly, right? How on the other hand we have gases, and these gases, their molecules or atoms are so further apart that for them changing positions is not a matter of problem. The bonding between these type of molecules or atoms is very less, right? That's why they can propagate here and there in space, right? So you all must be familiar with this thing. Now, the idea of temperature is very closely linked to all of this, right? Because when we talk about temperature, what do we mean when we say, so for example, I say you can classify temperature in two ways, right? You can say if something is hot or something is cold, right? So there are two ways that you can classify temperature: hot and cold. So what is temperature then? Temperature is, it is just, at the end of the day, it is uh, how hot or how cold a substance can be. So if this number is high, that means that it's the something is hot, and if the number is less, then we say something is cold. That is our association of numbers to the physical property, or degree of hotness or coldness of the substance. Okay, so it comes from the understanding of the molecular motion. So for example, if I'll consider a gas for an example, right? Suppose I consider a gas, for example. In this thing, this is a model of a gas, and the molecules are moving with some speeds. I'm going to assign the average speed of all of these molecules. I'll say that all these molecules move at an average speed of, you can say, 10. This is just an example, right? 10 meters per second. Then I have another gas whose molecules, if I measure the speed of these molecules, they move at 5 meters per second. All right. So it is this speed that is associated to the hotness and coldness of the substance. So, for example, if this if this gas, which I've drawn in white, is moving with 10 meters per second, that means it is at a higher temperature, or let's not talk in terms of temperature just now. It is hot compared to something that is moving slowly, right? So this means that the faster motion is associated to a hot substance, and slow motion of molecules is associated to the cold substance, right? So essentially, temperature is just a property that we use, or it aids us in computing the velocity of the particles. Or you can also say it helps us to compute the kinetic energy of a molecule, right?
Yes,
So,
I understand.
okay. So now we will also see the relation of temperature and heat as well, right? Okay, so the idea of temperature is more or less clear to everyone. You have to think in terms of the molecular nature of substance or matter,
Yes,
right?
clear.
So, okay. So the faster the thing is moving, we say that the temperature is higher. The slower something is moving, we say the temperature is low. And this temperature, it's actually a field, right? Temperature is a field that is spread across the, you can say, in the entire universe. And in this field, because from the definition of a field, right? So we have to completely understand temperature, you need to understand a field. A f- in a field, you can assign, pick any point in a field, and you can assign a number to that point in this field. So for example, what I'm trying to say is, if I consider a room, so this is a room, and let's suppose there are some windows in this room. Suppose there is a window over here, and there is something burning over here, right? So there's something burning over here. You can say it's a fireplace or something. Okay, so in this entire room, there is a field, and this field is called the temperature field. And this field is as though you can pick any point. So, for example, I'll draw my points with this color blue. Suppose I pick a point over here. I'm choosing a point randomly in this room, and suppose it's this one. This point will have a number higher than 0, compared to, for example, if I were to pick a point near the window. I can assign a number to both of these points, and because I'll feel more cold near the window, I'll say that this number is some less value, right? So I can assign some number over here. And similarly, I can assign a number at this point as well. And because near the fireplace, you feel hot, so you'll say that the number is a higher number compared to the window. And then in between, in the middle of this room or anywhere in this room, you can assign points, and all of these points will have some value of temperature, right? So that's a field, and more specifically, that's a temperature field where you can assign a temperature at every point in space. And the higher the temperature, it means that the motion of molecules at that place is faster, and the slower the temperature means the motion of molecules is slower. Now, this means that the temperature is directly related to the kinetic energy of a substance. So, for example, if I were to measure the temperature, I can easily or immediately compute the kinetic energy of that substance at that particular temperature, right? And there is a formula also for it, which at least for now you're not required to know, but you can compute the kinetic energy as 3/2 kT for an ideal gas. And then so at the moment, just think of it as you can kinetic energy and temperature are directly related to each other. These two are just constants, k and 3/2, right? So kinetic energy is then essentially, it's just temperature. It's just telling you the temperature of a substance, or the substance or the temperature is just telling you the kinetic energy of the material or any substance. Okay, so this with this we can talk about another thing, that is heat. Okay, so now when I say the word heat, you might think that okay, so there are two things. You might say the opposite of heat is cold, for example, but in reality, in nature, there is no such thing independently as cold. If I say something is cold, that means there is less amount of heat in that material, right? So heat is essentially the energy that is contained in the you can say in the motion of these molecules. So for example, if I say suppose I take again the example of some molecules, and I say that these molecules are moving with some speed, or I say that the temperature at this for these molecules is high. So these molecules will have some energy, right? And I can supply some energy to these molecules as well. If I apply some heating source or some flame, I apply some flame or burning to these molecules, what will that do? That is going to transfer some energy from this flame into these molecules, and this energy is known as the heat or heat energy, right? Now, heat is the only thing that flows in an object in reference to coldness. There is no such thing as cold flowing from one object to another. There is only heat that flows from one object to another. So you can say the heat is just the thermal or heat energy that is being, that you can say that it is thermal energy which is transferred from one object to another. Now the question is, from how do we know from what body to which body, right? For example, suppose I have uh, a glass over here, right? So I'm going to try to draw a glass, and there is some cube of ice lying next to the glass, right? And suppose that this glass contains a hot tea, right? Suppose it's a cup of hot tea or coffee, and here we have ice. Now, I said that thermal energy is going to be transferred from one body to another body. The question is from which one to which. For example, will it be transferred from ice to this cup of tea, or
No,
would it be transferred from the cup of tea to the ice?
I think big hot cup of tea to ice.
From hot cup of tea to ice. Okay, so the reason, one of the reasons that you can say for this thing is that, okay, so first, before I come to the reasoning of this thing, let me also define this as this heat always flows from you can say any hot object or from a region of higher temperature, right, to a region of lower temperature. And it is sensible, right? Because if you have to again think in terms of the motion of molecules, because so at this point you might say that, you know, why is it that it happens in this way? It does not make sense or anything, right? But it is actually very crystal clear that this is how heat should be transferred from something that is at a higher temperature to something that is at a lower temperature. If you think in terms of the molecular nature of these substances, you can see that if I let me bring this diagram on the next page. Okay, so in terms of the molecular motion, what is happening in this diagram that I just have over here, right? So for example, consider that you have a hot cup of tea over here, right? And next to it, there is some ice placed. The molecular motion of hot cup of tea is very high, right? So if I draw this in terms of molecules, then these molecules, I cannot simulate the thing over here. So try to use your imagination. The molecules in this hot tea, right? There are some molecules in this hot tea. These molecules are moving very fast, right? Because it's hot, and we have already understood the temperature, right? So if it's hot, that means the molecules have a very fast motion. Now, these molecules are going to collide with the molecules that are in air, right, around it. So there are some molecules of air. And what happens is that these green molecules, which are the molecules of hot tea, they collide with the molecules of air, which are these blue molecules. And essentially, up until here, we'll have so many air molecules, and these molecules will gain energy from these green molecules, from colliding with these green molecules. And essentially, so I'm going to draw the red molecules of ice. with this thing. So what has happened is that the heat was transferred first through the air or the environment, and then that environment carried that heat to ice, right? To the molecules of ice. And now when the ice starts gaining this energy in this way, eventually you'll see that it starts to melt because the temperature, because these molecules start moving faster. So is that
Understood.
does that make sense?
Yes.
All right.
Yes, sir.
Okay, perfect. Okay, so this is how heat is transferred, right? Heat transfer. And of course, we are going to study different methods of heat transfer as well. These methods are, we're going to get into those. They are conduction, convection, and radiation, which essentially have the same basis, right? This molecular nature of materials, substances. Okay, so that's one thing. Now, how can I measure the speed of these molecules? When I ask that question, what I'm essentially asking is, how can I measure temperature, right? So how can we measure temperature, or I can say speed of molecules? So when I say that if I ask the question measuring temperature or speed of molecules, is that everybody agrees with this, that temperature and the speed of molecules are uh, essentially one and the same thing? Does everybody
Yes,
agree with that?
I agree.
Yes, sir.
Okay, perfect. So, okay, now let's try to answer this question. Okay, so you can measure temperature uh, if you have any reference point to measure. So, for example, you can, even when we're measuring speeds or velocities of moving objects, we need a reference point. So we say that 0 means that the object is not moving at all, and we say that any number that is higher than 0, so 1, 2, 3 meters per second, 4 meters per second, means that the car is moving in the right direction. So for example, in the right direction or in the forward direction. So these are some things that we're assigning before doing the physics. So in the same way, you need a reference point for temperatures as well. And you can measure temperatures by using physical properties of these materials, because the physical properties of these materials are going to vary or change with temperature, right? For example, a very basic example would be if you look at this ice. If the temperature in this ice starts to rise, its physical property will change, right? But the ice will start to melt and it will turn into liquid, right? So the physical nature of the substance changed according to temperature. So we are going to use this thing, that physical properties of materials changes with temperature. So that essentially means the faster something is moving or the slower something is moving, it will affect its physical nature of that substance. I can give you some examples as well. Uh, a very basic example is expansion of a liquid with temperature, right? Or another very important example that we are also going to discuss is using the potential difference, right? And a thermometer that measures temperature in this sort of a way is called a thermocouple, right? Have you ever heard of the word thermocouple before? Anyone?
No, I never
Yes,
heard it.
No.
So
Okay.
it uses electricity to
Yeah.
measure the temperature, right? Because
Yes.
based
Yes.
on the temperature, uh, the the resistance I think changes.
Right. Essentially, it is the potential difference across. We use electricity exactly. So we use 2 points. We take 2 points and we measure the potential difference across those 2 points. Potential difference means voltage drop. So we measure that, and we can see that if there is some voltage drop across a junction, we say that okay, the the temperature is some particular value, and if there is a higher voltage drop, we say temperature is some other particular value. So um, let me just check one thing, if understanding thermocouple is a part of. Okay, so just knowing this much is enough. We'll see that we'll talk about the temperature scale, the thermodynamic temperature scale, and how can I construct, because essentially a thermometer is just a temperature scale, right? So for example, we say that 0 degrees is this thing, 100 degrees means this thing, right? So let me come to that very quickly. Thermodynamic temperature scale. Okay, so if you have a thermometer, you need two fixed points in that thermometer. So, for example, uh, we I'll give you an example of a thermometer where you have two fixed points as the lower point. You say that this is that 0 degrees Celsius. Now I'm using a temperature scale. I'm defining a unit for it, and this scale is the Celsius. If I know the spelling correct, I think it's SIUS, Celsius scale. Now, there are multiple scales of measuring temperatures. There is also another one which is called the Kelvin scale. And the Kelvin scale is used more often, and Kelvin is also the Kelvin scale defines the SI unit for temperature as well. But let's start with one of the easiest ways that you can measure temperature. Water is readily available to everyone, so we say that let's measure the temperature when water starts to freeze, right? Or you can say water start or ice starts to melt. That is the melting point of water, and you say that that's 0 degrees Celsius. So you take this point and you fix it, and you say okay, so this is the lower fixed point. Then you measure the temperature when water starts boiling, essentially just begins to boil, and you see that that temperature is 100 degrees Celsius. So we measured these two temperatures and we assign them values according to their scales. So we say in degrees Celsius, it is 0 when water melts and it is 100 when water boils. Now, everything in the middle we can it is just in degrees Celsius. So we go from 0, 1, 2, 3, 4, and so on up to 100 degrees Celsius. Now these 0 and 100, these are the fixed points, or you can say these are the reference points, and we can use these points and then measure the temperature in between. So essentially you have to calibrate your thermometer with these 2 points and then divide this scale into 100 equal parts. 100 because the maximum number is 100 degrees Celsius on the scale and the minimum number is 0 degrees Celsius. Then you start dividing it into those 100 equal parts. The emphasis is on the word equal, right? So the scale should be divided into equal parts, and the number of parts depend on the minimum and the maximum value on the temperature scale. So okay, so is that clear for the class?
Yes, clear.
Okay, all right. Just give me a second.